Hello everyone. Good morning, afternoon, and evening to everyone depending on which time zone you're calling from. I'd like to welcome you all to today's webinar titled Boost Your Circuit Simulation Performance with the New PSpice Engine. My name is Kishore Kanani and I'm the Product Marketing Director for the OrCAD product line at Cadence. So as you all know, filters, amplifiers, linear and switch mode power supplies, and any other analog and mixed signal designs require rigorous analysis and debug to ensure that they will meet the performance specifications that have been specified. Failures due to violation of component operating limits, yield problems, component failing due to overstressing, all of these types of failures can cost you in engineering productivity, missed schedules, design predictability, as well as cost. The Cadence PSpice Simulator and the PSpice Advanced Analysis address all of these issues. In this webinar, you will be introduced to mixed signal simulation, stress analyses, design optimization, sensitivity, Monte Carlo analyses, and other analyses using the PSpice Simulator. Just want to let you know that this webinar is also being recorded, and the recording will be available to all of you if you would like to review the slides again, or if you would like to share it with your colleagues. Also, throughout the webinar, you can submit any online questions through the Q&A box on the right, and we will try to respond to all of them during the presentation. We also will have a Q&A session at the end of the webinar, so if you want to ask any questions at the end, we'll be more than happy to answer them at the end also. So feel free to submit any questions during the presentation if you would like any clarification on any of the topics that we are presenting. With me today, I also have John Carney, who will be the main presenter of this webinar. Just to give a quick overview on John's bio, John is a PCB staff applications engineer, and he's been working with Cadence for the past 18 years. He has a EE degree from Southern Illinois University. He started with OrCAD about 1 month before the OrCAD MicroSim merger, so he has a very long history with PSpice. He's been supporting analog and mixed signal customers with their design and simulation challenges for the past 10 years. So let's start the presentation. All right, the topic that we're going to be covering in this presentation is I'll start off with a quick PSpice overview, and then I'll hand it over to John, who'll go into some multi-level system simulations in PSpice. So he'll talk about all the different abstraction levels of modeling that are available in PSpice. He'll also talk about system modeling extensions that have been included into PSpice in the latest release. So he'll talk about how you can actually do the system level simulation with PSpice also. In addition to all of that, we'll also talk about how you can improve your design cost, productivity, reliability, and manufacturability using the PSpice Advanced Analysis. So let's start off with why PSpice. Question that's been asked quite a few times from us is why PSpice? PSpice is the most accurate SPICE simulator for mixed signal SPICE-based circuit simulation. So if you're looking for accuracy, there is no other simulator other than PSpice that can provide you the accuracy in simulation. It also has the largest simulation model of availability out there. It's had over 33,000 models available for simulation. In addition to that, we have a very comprehensive ecosystem. So most IC vendors today provide PSpice simulation models. So in other words, like TI, ST, all of these IC vendors today, they provide the PSpice compatible model. So if you're starting off a simulation, there's no easy way to start off other than just going and start using a PSpice model and going with it. Also, we have very tight integrations with Virtuoso, Allegro, and OrCAD PCB design flows. So if you're starting off on the IT side with Virtuoso, we also have links where you can bring those models into the Allegro side or the PSpice side and actually simulate with them on the board. We also have very tight integration with system-level solutions like MathWorks. So if you have a model that's an algorithmic model or a behavioral model, you can also bring your MathWorks model into PSpice. So you can have a model in C, C++, SystemC, Verilog ADMS. All those different types of abstractions can be brought into the PSpice domain. And John will be talking more about that during his presentation also. In addition, PSpice provides the most comprehensive advanced analysis capabilities to enable customers to reduce the design cost, improve reliability, productivity, and yield. So we'll talk about Monte Carlo analysis, optimization, stress analysis, all of these different analysis types that will help you improve your reliability. Lastly, we have just introduced PSpice.com user community for customers to share their models. If they want to chat with other engineers, or if they would like to chat with Cadence experts. So this user community enables customers to find any PSpice collateral on the web by just going to the PSpice.com site. Let's talk about some of the key differentiators of PSpice. So one of the main key differentiators of PSpice is the PSpice Probe. It's one of the most popular analog and mixed signal debug environments. So it enables customers to view waveforms in multiple plots, cross-probe from schematic, make complex measurements, as well as it has an expanded set of mathematical functions if you want to make some complex measurements. The advanced analysis capability is unique in an industry where we include stress analysis for calculating component stress, yield for using Monte Carlo analysis. We have optimization where we can optimize your design based on circuit parameters, as well as parametric plotting, sensitivity analysis. So all of these analyses go into the advanced analysis bundle. In addition, we also have model editor capabilities. So in other words, if you want to create any models using some predefined templates, and John will go more into depth on some of these templates, we provide modeling templates where you can go in and create MOSFETs, LEDs, magnetic models, Zener diodes. All of these components have templates provided to you so that you can take datasheet information and very quickly create a model for simulation. Similarly, we also have a stimulus editor. It's an interactive graphical environment where user can create pulses, or they can bring in hardware waveforms, very easily create a stimulus for your design. So basically what PSpice does is provides a single design entry for simulation, analysis, as well as PCB implementation flow. So next, like I talked about earlier, we've introduced PSpice.com community site. So basically what the PSpice.com is, it's a user community website for designers, partners, students, all of these customers that can go to this site and access any of the collateral that is related to PSpice. Also, a partnership with TI, WebBench, also enables designers to search for any TI component, their relevant reference design, and they can also simulate that reference design on the web, all using the PSpice, OrCAD, and the PCB layout tools. So basically what PSpice.com is your one-stop shopping for PSpice models, app notes, design examples, as well as video tutorials. So if you have not signed up for PSpice.com, I would highly recommend you to go to the PSpice.com and sign up over there, because you can chat with many other PSpice experts on the web. That being said, I will start off. I'll do a quick polling for you guys. So I'll just wanted to find out, are you aware of PSpice.com community site? So please go ahead and answer that question whenever you get a chance. Wow, looks like most of you are aware of it. That's great. And the people who are not aware, please go to that website after this webinar and sign up for it. Next question. This is an interesting question. Which analog or mixed signal simulator have you been using? So check all of them that apply. In this case, are you using PSpice, LTSpice, Multisim, Simplest, or some other simulator? Wow, looks like most of you are using PSpice and LTSpice, so that's great. So that's what we kind of expected. The last polling question before I hand it over to John is, what is your key criteria for choosing a circuit simulator? Is it price? Is it simulation performance or convergence? Is it the availability of the models? Or is it ease of use? And maybe there's something other, so feel free to file other if that's the other one. But it looks like most of you are looking for simulation performance, convergence, and model availability. So that's good feedback over there. That's excellent. So thanks for taking the time to provide the polling questions. So now what I will do is I will hand it over to John, who will go into much more details of the system-level simulation, modeling extensions, and then go into the advanced analyses. So there you go, John.
Thank you, Kishore, and hello, everybody. Welcome. So I'm going to begin talking about multi-level system simulation in PSpice, and this is our new marquee feature, new enhancement that we've added recently, along with several other ease of use and functionality enhancements that I'll be talking about. So when it comes to a system, everybody is aware that things are getting integrated more tightly, right? A long time ago, the analog circuit that you simulate with PSpice may just be a handful of discrete devices. And now these discrete analog circuits are getting more tightly coupled and more designed in with large ICs, integrated ICs, multiple printed circuit boards. And the desire and need to simulate the analog and the digital domains concurrently is becoming more and more prevalent. The challenge with that is the more devices that you try to stick into a simulation engine, it becomes prohibitively slow to try and simulate a multi-PCB system all the way down at the transistor level inside every IC. That's just prohibitive. It can't be done. So there are different levels of models and abstraction of models to address the different levels of the design. So there can still be SPICE models for discrete components, but there can also be all the way up to system models that may model a large IC or a bunch of ICs collectively. And there's different levels of models in between. So you go to higher level of abstraction to increase the simulation time. You may lose a little bit of accuracy all the way down to the transistor level inside the IC, but at a system level, that's not very relevant. And here's an example, a typical example of what a lot of people are using this for in PSpice today. So if you imagine a power supply, you can now have a digital software-controlled power supply where you'd have a power stage, an output stage, and then some sort of A to D feedback loop into some sort of microcontroller. They can then sense that output and then using software algorithms drive the power supply. Okay, so now with the ability to do mixed signal simulation in PSpice, this can be achievable. So this will allow you to model that power supply not only under the fixed conditions, but under variable conditions like temperature variation, time variation, and aging of that circuit. It also could enable you to have a single power supply that you can vary to manage multiple control loops. So how is this done? So if you were to think of a system, a system could be a single PCB, multiple PCBs. There's going to be different devices and different circuits in that design that you are going to need to model at different levels of abstraction depending on where you need the details at. So it could be your traditional SPICE level models all the way down at the bottom modeling discrete devices. You could have some mixed signal SPICE and gate level simulation models for somewhat larger mixed signal technologies, all the way up to the top where you may have a system on a chip or a full package model where you could then start to begin looking at system macro models. And so it's a different level of model abstraction from physical implementation to circuit level, gate level, behavioral, functional, all the way up to an architectural model that can represent pretty well anything. And so how does that map to what can be done in PSpice today with our new support for mixed signal system simulation? So if you were to consider all these different levels of model abstraction, PSpice can now support and enable you to use all of them. So if you have a system macro model developed in SystemC for an architectural model, we can now use that in PSpice. If you have some sort of gate level model with C, C++, PSpice mixed signal devices, you can now use that with the PSpice simulator. And we still support all the traditional analog and SPICE models that you've been using today. So we basically just now expanded the simulation engine and its capabilities to absorb all these different types of models, so you can now truly model your system at any level of abstraction that you need. So how did we do that? So PSpice has actually always been a very powerful mixed signal simulator. It had an analog matrix solver, and it had a digital event solver with 6 different logic levels, with Z level being the strength. The challenge was the digital models that PSpice could use weren't readily available and very popular because the modeling language was a kind of an internal language. So what we did is we looked at what sort of devices would people want to use for digital simulation along with the traditional right-hand side analog simulation that we had. So PSpice has always supported diode models, inductor models, MOSFET models, bipolar transistor models. And then we started looking at all the digital types of devices that would be out there, like random access read-write memory, stimulus generators, flip-flops and latches, file stimulus, A to D converters, read-only memory. And we started looking at what sort of models were available in the market for those sorts of devices. And a lot of those digital devices could all be modeled using C, C++ digital models, or a SystemC model of that particular device. So we enabled that simulation engine to understand and comprehend and then use those types of models for all those devices. So now if you need to model something like memory or a D to A converter, typically you'll have, or you may be actually designing those converters, those devices, so you'll have access to the SystemC or C++ digital model. So now we can use that in the PSpice simulation engine. Additionally, we've enhanced the analog side of the simulation engine to also understand things like C and C++ behavior models for analog devices, and also Verilog A and ADMS configuration models. So now, depending on the level of model that you have and the accurate simulation that you need to achieve for your system, you can pretty well model any type of device that you now may have in your design or your system that you need to analyze. So here's an example, again, using that software-controlled power supply that I mentioned before. So if you have your schematic now in place, in addition to selecting a component and seeing a SpiceBase model associated to that component, you can now select that component and look at a C++ DLL model that can be assigned to that particular device. And the whole system can be simulated using the singular PSpice engine. The way we've enabled our customers to do that is actually very easy and straightforward. So it's a very powerful set of functionality, and we have a PSpice model code generator that's available from the model editor. So now, as a user, all you need to do is open up this form, specify the name of the part that you need to be modeling, specify the part type, whether it's a digital C++ code, SystemC code, analog code, Verilog A or ADMS code, specify the type of device that the model is going to represent, whether it's a generic device, voltage-controlled voltage source, generic 3-node device, generic 2-node device, function-dependent current source. And then you can specify the global, instance, and model parameters that need to get passed into that device from the schematic. And then that is going to go out and read that code, and it's going to produce a DLL file, basically a wrapper for that DLL file that the PSpice engine can now interface with. And then the final result of that is going to be a new LIDE file with a pointer to the DLL file that you can create a schematic symbol for, or if you use one of the generic 2 or 3-node devices, it'll create a schematic symbol for, and it'll place that right into and then you can have that in your library that you can place into the schematic. And once you have that in place, you're now ready to do mixed signal system simulation. So I'm going to briefly switch over to the schematic editor tool and show you how that looks in the design. So if you have a particular design, and if you had some sort of software-controlled PWM block, if you were to launch the model editor for that and look at the model, you still have your typical dot subcircuit statement, but now inside that subcircuit, you now have a pointer towards a C model, which is a DLL file on your disk. So now in addition to PSpice knowing where all your SPICE libraries are at, PSpice is now just going to have a reference to where these DLL files are located. When you run that simulation, you'll now get a mixture of digital output along with analog output. And if we were to zoom in here to a very tight area, you can see the level of fidelity that you're able to achieve with both analog and digital simulation with the software-controlled power supply. Okay. So that in overview was our mixed signal simulation ability. So that's a very large enhancement that we've recently added to the PSpice tool, and we plan on continuing to enhance PSpice as a full mixed signal system simulator. In addition to that, we've added a lot of functionality in the past couple of releases in terms of just ease of use and the simulation engine itself for performance, accuracy, and convergence. So for those of you that are using the OrCAD schematic entry tool, these next couple of features are going to be for you. And these are not all of the features we've added, but we've just picked some of the highlights. If any of you are interested in seeing all the features that we've added, feel free to contact us so we can go through them. So the first thing we've added is the ability to now embed PSpice directives right on the schematic page as a text-based comment. We know a lot of powerful PSpice power users out there would always use a PSpice argument, and they'd have it just as a text file in their netlist directory. Now you can just embed a text file using the @PSpice statement, put it on your schematic, so that way you know what the directives are, and anybody else referencing that circuit in the future know what those directives are. So now you can do that without having to go into a text file. We've also added other ease of use improvements for people who have to create a schematic for PSpice. So we've added a quick place PSpice menu. So if you go under the place menu under PSpice component, you'll have quick access to all the salt and pepper devices that you typically add: capacitors, diodes, inductors, resistors, sources, passives, discretes. We've also added a HTML-based PSpice part search. So when you get PSpice, as Kishore mentioned, it comes with models from thousands of models from hundreds of different vendors out there. And so now what you can do is you can now use the PSpice part search to parametrically search for these models. You know, you can say, I'm looking for an op amp with these types of characteristics, and it'll search through descriptions of all the models that come with the tool and give you the part or parts that match that source. And then the final thing is model assignment from the schematic. So if you have a schematic that may be targeted at a PCB and you now need to simulate that with PSpice, you can go through that schematic and select the components and link those components to an existing SPICE model that you may have on disk. We've also introduced PSpice modeling apps. These are some examples that we have now. We plan on continuing to add more of these things. So if you need to do something like add a piecewise linear source or a Zener diode or a transient voltage suppressor or a transformer, you can launch these model apps directly from the schematic editor. It'll bring up a form that allows you to quickly input the parameters of the model that you need to create. Simply input the form, hit the place button, and it'll build the model on the fly, attach that model to the part, and attach the cursor, the component to your cursor, and you can place it directly in the schematic. So this would be a huge time saving instead of having to go out and figure out how to figure out SPICE syntax for a model or go find a particular model they need to have. So here's a couple examples of these things. First, we have the voltage control oscillator app. So you can use this to create an instance, or you can modify the parameters of an existing instance on the page. And when you go into this app, we support sinusoidal, triangular, and square wave. Once you select which type of oscillator you want to use, you fill out the parameters of the oscillator. And in this form and in all of these forms, we give you nice text-based description of what the app's going to do, what you need to fill in. Once you specify the parameters, you hit the place button. It'll place that component on your cursor, and you place it down. The model's attached. It's automatically referenced by the simulator, so you don't need to set up any paths, and then you can run the simulation. We also have a switch app. A lot of people struggled making switches with PSpice, so now we just built an app that allows you to do time-controlled, voltage-controlled, and current-controlled switches, all of which can be normally opened or normally closed at T-start. Okay, so we have time-controlled, voltage-controlled, current-controlled switches. And you can even include hysteresis-controlled switches. We also have piecewise linear sources. So instead of having to go to a text file to fill in your piecewise linear sources or use the stimulus editor, you can launch the PWL source simulator, and you can just fill in the time steps in this form, or you can hit this button here to add additional PWL points, and you can even reference an external file that has those PWL points in them. So let me just briefly switch to the tool to show you how easy that is. So under the Place menu, for the PSpice users, everything you need is now under this PSpice component form. So you have the modeling application or the search. So if you go under modeling application and choose sources and choose independent sources, it'll bring up the independent source app where you can choose between pulse, sine, DC, exponential, FM, impulse, and you can choose voltage and current source. Once you specify the parameters that you want, you can just hit place and place the part on your schematic page, and you're done. In addition to the schematic editor enhancements and the mixed signal enhancements, we've also put a lot of work into the underlying PSpice simulation engine to deal with performance, accuracy, and convergence. And again, these slides are covering some of these features. We actually have more detailed slides if you're interested in them. So we now have added a new speed level in PSpice. So we add speed level 3 that allows the simulation to run a lot faster, and it allows you to model devices switching at faster speeds without introducing convergence errors and without sacrificing performance. We've also introduced the ability to have PSpice run with multiple processor threads. So if you have a simulation that historically was taking a long time, in the simulation settings, you can tell it to use up to 4 processing threads. Before, historically, it would only use half of the threads available, leaving the other processes available for other things the system may be doing, but now you can tell PSpice to use as much of the capacity that can be used. We also now support 64-bit probe data accuracy. So if you have things that are happening maybe out at the 10th decimal place, we can now model that. We've also added more enhancements for convergence issues. So we added the ability to enable auto convergence quite a few releases ago, and now we've added enhanced auto converge algorithms, things like an integration method, node value limiting, and relative tolerance options. Once you run the simulation, we've also added some measurement applications that are very specific, but we noticed these were things that people were having to use hand-based calculators or spreadsheets or other outside of the tool applications to accomplish. So 2 of them are frequency response analysis. So if you need to calculate the open loop gain for switching power supply using transient analysis, you can use a frequency response analysis to do that. So you basically sweep a circuit across a range of frequencies, give all those AC simulation results to the frequency response analysis, and then it'll use Middlebrock's method to calculate the frequency response analysis. We also have a hysteresis core loss calculator that enables you to measure the steady state loss of energy in a magnetic core for power supplies. So you basically, again, run a simulation, fill in the core values, specify the start time and the end time and the core value, and then it'll calculate the core loss for you. So this is kind of the direction that we're going with PSpice, is not only giving you a simulation engine, but also giving you powerful apps that you can use to post-process the data that you get from those simulation runs. Another application that we've created is a PSpice simulation report. So typically after you run a simulation, you need to include some sort of report that you need to embed with the design or share with other people. And so now we've made that a push button thing, so you can generate a report. It'll create an HTML report listing all the average RMS and peak values of colted burns from power run in the design. And you can even set up an option so that that can be run out of the box as a default. And these 3 apps that I just mentioned are all open source. So PSpice can now be automated using Tickle automation. We have a Tickle-based API. And these applications are completely open source, so you can look at the source code for them. You can use it as a basis to write your own Tickle automation. So before I go into advanced analysis, we're going to kick off another polling question.
So here we go. What types of designs do you normally simulate? So let's check all of that apply. Do you do power supply designs, mixed signal designs, filter designs, or system level designs, or something totally different? It looks like many of you are saying power supply designs as well as mixed signal designs, so that's great. Still coming in, still coming in. Yeah. All right. Thanks.
All right. Thanks, everybody. I'll go ahead and continue. So now I'm going to talk about the advanced analysis capabilities in PSpice. And these advanced analysis capabilities will allow you to use PSpice not to just do functional simulation, but now look at it as in terms of improving your design cost by maybe removing components or using lower price components, improve the productivity of you as a designer by allowing you to design your circuit quicker, and also to figure out the reliability and manufacturability of that circuit that you're designing. So why would this be important to you, right? If you were to think of a traditional SPICE circuit that has a handful of discrete devices, those discrete devices on that schematic that you're simulating in the netlist all have a value that you've assigned to them, a 1 k ohm resistor, 1 picofarad capacitor. But we all know that there are other parameters that are going to vary in that circuit simulation, and that those components, if you were to manufacture 1,000 of those designs, you're not always going to get exactly a 1 k ohm resistor or a 1 picofarad capacitor. Okay, and you know that those component values are going to change over temperature, over age, as currents go up and voltages go down. There's going to be all sorts of variability on that circuit. It's not always going to be 100% exactly the values that you have in your design. So the advanced analysis engines in PSpice allow you to use those values to your advantage. You'll be able to determine are things being overstressed, or you can drive those values to achieve a better operating circuit. So I'm going to go through the different types of advanced analysis that we have. So we have a sensitivity analysis, which can help drive cost. The sensitivity analysis is going to allow you to take those components in your design and look at the desired output that you have on your circuit and determine which components and which parameter of those components have the biggest impact on that desired output. We're going to talk about productivity in terms of the optimizer. So if you have a given circuit, the optimizer is kind of going to allow you to reverse engineer that circuit, and instead of you having to sit down and experiment with component values to achieve the desired output, you can tell the optimizer what you want the output to be, which component values you want it to vary, and it'll do all the hard work for you and give you the final result. Predictability in terms of parametric analysis. Parametric analysis allows you to control sweeping parameters for every component and every parameter of the design, do thousands of simulation runs to see if there are any strange or unique corner cases that you need to be aware of. Reliability in terms of smoke. So there may be things like power dissipation, junction temperature, collector-based voltages in your design that if you do not model these things and take them into account, you may have what could be a functional circuit that can simulate, but the real physical device model could fail because you could be violating or pushing it beyond its limits. And finally, we have Monte Carlo or yield analysis. So again, if you think about this circuit that you've designed, and you may have 50 devices in that design, if you were to go manufacture that, there's different tolerances of those devices based upon how expensive or how cheap of components you're building. The random combination of all those tolerances of components that the pick and place machine puts down is going to vary the output and the performance of that circuit. So the Monte Carlo analysis allows you to sweep a circuit across maybe 1,000 simulation runs, a couple thousand simulation runs, randomly varying those component values, based upon parameters that you define, and then it'll let you know what your yield is going to be. Okay, so the PSpice Advanced Analysis takes PSpice simulation to another stage to help you determine if you can reduce the cost of it, you can increase the productivity of your circuit, or measure or increase your yield. So this is what the sensitivity analysis GUI looks like. It allows you to look at all the components that you have in your design and then identify a parameter of those components that's going to be varied for the sensitivity analysis run. This screenshot here is showing value, but you can really vary any component value that you have. In the bottom portion of the screenshot is showing different measurements that are being made on that circuit. So to do sensitivity analysis, you draw your circuit, and then you run a time-based or a frequency domain, you know, an AC or DC-based simulation, and then you can put in specific measurements that you're interested in. So for example, shown here is the max dB of the V-load output, or the bandwidth of the V-load output of a particular circuit. The simulation is then going to run, the sensitivity analysis is then going to run, and it's going to vary these component values based upon the parameters that you define in the design, which I'll show you in a second. So you'll have a resistor, and it'll have a positive tolerance value and a negative tolerance for the value. So it knows that resistor's value can sweep within a range, typically a Gaussian type of distribution of the range. It's then going to make these measurements across all these different simulation runs. And what it's showing you now is that this particular component, R4, has a large impact to this particular measurement. Or stated another way, this measurement, max dB V load, is very sensitive to the value of this R4 component. On the other hand, R1 has very little impact at all in the measurement value for this measurement. So this could help save you cost, because this way you'll know that for component R1, you can go buy some lower price components that aren't very precision. It doesn't really matter how much this value swings. But for R4, you may want to invest in a highly precision set of resistors for that particular device. So I'll show you more of that in a demonstration. And then there's circuit optimization. So if you imagine that same circuit in your head that you're typically designing, instead of you yourself trying to figure out what's the best value of this feedback resistor, or what's the best value of this capacitor in the design, you can turn that on its head, and you can tell the simulation engine, these are the components, and I want you to vary their values, and I want to achieve this output. I want to have this voltage output, or this bandwidth output, or this noise value at the output. And so the simulator will go through, and it'll vary the component values within the range that you specify, and it'll try to achieve those values in the circuit. So the closer it gets to achieving the values, it'll continue to hone in and zero in on that simulation solution. So it finds the optimal value of component values. It simulates, it evaluates the results, it adjusts component values, and it tries to converge upon a solution. And so this can be used to design a first run of a design, or you can take an existing design that you may already have done. You may have a layout already completed, right? And you now may have the option of maybe just placing different values of resistors or discrete components into that circuit to redesign or redesign that circuit for an existing design, or maybe different regional requirements. So that's another advantage of PSpice, is that the same circuit, the same schematic engine that drives PSpice drives your PCB layout. So you can use this optimization engine to keep the same layout, vary the components that are placed in that layout. And it saves a ton of time. You know, it's automated. This is one of the things I love about automated simulation engines. You can give this problem to the simulator. It can run 1,000 simulation runs. During that time, you're thinking about more important things. So how does the optimizer work? You basically give it a circuit, an analog circuit. You give it design targets, power, rise time, GVW, and it'll go through and vary the value of the components and other parameters to achieve the goals that you specified. Okay, so you could basically have a before simulation, and then after simulation run, or reuse an old design to retarget its performance. Another option is if you have a given circuit with a given layout, you could tell it to target one country's power level specification, bandwidth level specification, noise specifications, and it'll optimize the circuit for that, and then you can retarget it to a different country with different specifications, and you're not redesigning the circuit manually. So here's what the optimizer looks like. So again, you have your selection of components in the design that the circuit can optimize, and you give it the parameter that it can optimize, and then you have your measurements, power V out, decibels V out, and instead of you give the circuit simulator a range that you want it to be in. So you say, I want the power V out to have this value. I want the dB of V out to have this value. And then the circuit simulator will start off with the original values of the components in the design, and it'll run multiple simulation runs, tweaking these values of these components until it converges upon a solution. Once you have that solution, you have the final value of the components that achieve that exact result. So if originally you had a 1.2K resistor, you end up with a final value of a resistor and capacitor values that achieve that result. And there's YouTube videos on this that you can watch. The next advanced analysis ability that we have is smoke analysis, and this is another thing that's unique in the industry. With the model editor that comes with PSpice, and with a lot of the libraries that come with PSpice, we not only include the basic SPICE models, but we also include smoke parameters, such as, like I said, power dissipation, collector base voltage, junction temperatures. So the smoke analysis is going to run that simulation, and then it's going to measure it against all the peak, RMS, and average values of all these different operating parameters of the design. And it's going to let you know if you have devices in your design that have some sort of parameter and what percentage those are being operated at with respect to the average peak and RMS value. Okay, so this can help in thermal design, and we call it smoke because the basic idea is you know, you may have designed a circuit that functionally is going to work, but if you're really going to power that up, it's going to catch on fire because you're pushing too much current through a device. This also allows you to specify derating for the design. So we know that, you know, a certain device may be able to take a spike in temperature or a spike in current for a short period of time, but if you extend that, device is going to degrade and the current's going to flow through it even more, and it causes a kind of downward spiral sort of situation. So the smoke analysis allows you to run it with or without derating. And with this advanced analysis, again, you see all the components in the design, and you can cross-probe from here to the schematic design. You can cross-probe from smoke analysis, sensitivity analysis, optimizer, Monte Carlo, all those things are directly linked to the schematic editor. We also have parametric sweeping. So all those other advanced analysis, those are sweeping the parameters based upon the tolerances of the components that you define to achieve a targeted measurement result. But let's say you yourself have something in your mind that you want to sweep a component value through a range of values. And then you may have 3 other components with parameters that you want to sweep as well. So the parametric sweep allows you to define the values and the parameters that you want to sweep across any range of values, and then run the simulation. And so you could sweep 3 component values through a range of 100 values, and the parametric sweep will run every single simulation run with every combination of value, and then it has a nice user interface that allows you to build and look at the waveform results or the range of waveform results across those range of values. So once you swept several values, you can define what you want to have as the x-axis, what you want to have as a y-axis, and then what you want to have as a variability range of waveforms. So this way you can switch it across any parameters you want to ensure there's no unusual circuit behavior. And then finally, we have yield analysis, which can introduce cost savings in your design. So you have your circuit, and again, you have your measurements, which are shown here in the screenshot: max dB of V load, bandwidth of V load. So you have your circuit, and you have your measurements of that circuit that you care about. You have discrete devices in your design that when you manufacture a couple thousand of these things, you're not always going to get the exact combination of the devices that you've placed in your schematic. Their values and other parameters are going to vary as they're picked and placed and put in the design. So Monte Carlo yield analysis is going to randomly vary those things and show you what your yield is going to be with the random combination of those devices. So let me show you what that looks like in terms of in the tool. So if you had a basic circuit like this with all these devices in the design, there's a parameter block that can be placed along in the circuit that defines capacitor tolerance, resistor tolerance, inductors tolerance. So all these devices have a tolerance value plus minus using this parameter, plus minus 10%, plus minus 10%. You can globally apply it, or you can specify explicit values for each particular device if you have them. So it can be global, or it can be down to each unique device value. And then after you run the simulation, you can then go into the advanced analysis form. So I'll first talk about sensitivity analysis. So in terms of sensitivity, you have these different measurements that you can define. Just like you create measurements on the waveform in PSpice, you can create measurements to be used for sensitivity. And so what this is telling you is that for this particular measurement, based upon the AC simulation, the max dB of V load, the component C6 has a very large impact in that measurement. If you were to select that component and find it in the design, you can see why that value, that capacitor, has a large impact in that measurement. Whereas these resistor values have minimal or no impact whatsoever in this desired measurement, okay? So this is going to let you know from a cost perspective that you maybe need to buy or use your high precision components out of your bins first for these, and then you use your low precision values for that. And you can see the sensitivity analysis for multiple different measurements all at the same time. So you can make as many measurements as you want in your design and run sensitivity analysis on that. The next advanced analysis is the optimizer. So the optimizer can use the exact same measurements that you ran with sensitivity. And you can run these in any order. You can run optimizer first, then sensitivity, or sensitivity first, and then optimizer. So the optimizer is basically an engineer in the box. It's a reverse engineer. So for this example, we're telling the optimizer they can optimize components R8, R6, and R4. And the value that it can swing is the resistor's value, okay? You can add as many components as you want in the design to optimize. And again, you have these measurements. So now what you're telling the tool is that for this particular measurement, that you want it to be between 5 and 5.5, and that's a constraint. And you can even weigh these things, add a weight that this thing has a much higher weight than this other measurement bandwidth of B load. You can also have the max B noise, and you want that to be a max value of 3N. So you can specify minimum max, goals, targets, and constraints for as many measurements as you want. And now you're telling the tool, tweak these resistor values until you achieve the results that I've defined. So the simulation engine is going to start out at simulation run 0 using the current values of the resistors that were in the schematic, and then it's going to start running simulations. As it simulates, it's honing in on simulation values. So it's not just blindly varying things. It's taking measurements, and it's knowing whether it's converging on a solution or diverging from a solution. So it uses that, and so you can see as you go through the different simulation runs, you can see what the original resistor value is, and then what the current resistor value is. And if you were to extend that all the way out to the last simulation run, you can finally see what the exact or ideal value of these three components needs to be to achieve these exact measurements or performance of the circuit that you're interested in. Okay, and that's using a modified LSQ engine. Next, we have smoke analysis. So you can add smoke parameters to your models in your design, or you can use the out-of-the-box PSpice components that have smoke parameters built in. And so this user interface is going to basically show you that for these devices in the design, so for example, this resistor has maximum power dissipation. This transistor has maximum power distribution. This one has maximum junction temperature. This one has max CB voltage. So these are other parameters in your design that may be of interest that if you didn't run the smoke simulation, you would never know what the effect of the voltage and currents that you're running through the circuit are going to have effect on these parameters. And the parameters are all average, peak, and RMS. So this plot is basically showing you that you have this component R9 in the design, and it's operating at a value well over its rated value. Okay, so it's rated at 200 M. It's operating at about 277. This Q1 has a peak value of 20. It's operating only at 11. So these devices down here, the ones that are green, are safe. These devices up here, even though you have a correct resistor value, you probably need to go get a resistor value that has a higher tolerance for maximum power dissipation, because you're just putting too much voltage and current through that resistor. It's going to smoke. So within this design, you can even run this, and you can include derating or not include derating. If you take the derating out of the design and rerun the analysis, you get a different result. The final advanced piece of advanced analysis is Monte Carlo. So again, you have this circuit, you have these component values in the design, but we all know if you were to go manufacture a couple 100,000 of these things, you're not always going to get these exact values at this exact combination. So Monte Carlo is going to go through and just run. In this case, I think I ran 1,000 simulation runs. No, I did 500. There's no limit to how many you can run. And you can see that this graph up here is showing you, for example, max CB load, that out of those 500 simulation runs, approximately 80 of them had a measured value between 8.9 and 9.2. So random combination of those component values are giving you this measurement for the max dBAV load. You had about 20 of them with combination of component values that had a measurement between 8.3 and 8.65. So if your minimum acceptable value for this circuit is 8.9 and your maximum acceptable value is 10, this yield graph is basically letting you know that you have a large number of simulation runs. Specifically, your yield is only 78% of those devices that are actually going to be operating within your acceptable min-max range. All of these are garbage. All of these are garbage. Again, letting you know that you may need to go put some higher tolerance components in your design, or maybe redesign your circuit so you get a better yield. And you can calculate that across multiple measurements at any given time. So if, let's say, if the ideal or acceptable value for bandwidth was between 1.39 and 1.64, then this is letting you know 100% of the combinations of those component values is going to produce acceptable values. Okay, so the more you run the larger number of simulation runs you run, you're going to get a nice bell curve here letting you know your yield. So that's an overview of the advanced analysis capability that's unique for PSpice in the marketplace. No other simulation tool has the ability to do basic analog simulation and mixed signal, and then bear your component values with targeted measurements of optimize your yield, smoke, and sensitivity. So just in summary, using PSpice Advanced Analysis, it's unmatched in the ability to analyze your circuit and then drive your circuit for performance, yield, and cost. So now before we open it up in Q&A, I think Kishore has some more polling questions that he wants to do.
Just one more.
Just one more.
So what John showed you on the advanced analysis, we'd like to find out is which advanced analysis technique would help you improve your cost, productivity, reliability, or help you optimize your design. So please select one of the ones that you can think that can really help you out on this one. Oh, looks like the sensitivity and optimizer are the key ones. Actually, smoke analysis looks like it's a great one too. So it looks like smoke analysis is also a great way you guys are telling us that it's going to help you improve your design reliability. Excellent.
Great, thank you. And then really quick, I'm going to gloss over to the PSpice.com website. Again, I really invite everybody to come visit this PSpice.com website. It's a dedicated website hosted by Cadence that's all PSpice and nothing but PSpice, that has a lot of great movie resources, application notes, and then there's a user forum. We know people have been asking for a PSpice user forum for a long time, where you can log in and you can post your own questions and comments and dialogue with other PSpice users all around the world. So in summary, before we open it up for Q&A, so PSpice is the most accurate SPICE simulator out there for mixed signal SPICE-based circuit simulation. And we have a very large ecosystem out there. Considering that it's the most popular SPICE-based simulation tool, every IC vendor wants to have SPICE models that run with PSpice. So if you need to simulate a circuit from a vendor, more than likely you're going to be able to get a PSpice model from them. And with the advanced analysis capabilities that I've shown you and the ease of use abilities that I put in the schematic editor, we're hoping to continue to enable our customers to really be productive with PSpice. And it really is an unmatched solution when you combine it with the advanced analysis abilities. So we've been putting a lot of resources, R&D resources. We've almost tripled our R&D staff with PSpice over the past couple of years. And you should notice with the addition of the PSpice.com website, with these webinars and mixed signal, that we have a long and high-looking future for the PSpice tool. So we hope to hear back from a lot of you on what you thought of this webinar, and hopefully you guys can reach out to us and we can do more focused demonstrations for you and your organization. Thank you. Now I'm going to open it up for Q&A.
Thanks, John. Thanks for that presentation. Actually, we had a very, very interactive Q&A section going on, so I'm pretty sure most of you saw all the responses that were coming in. There were a lot of great responses, and Alok Tripathi and Gil Reeves have been answering those questions, so hopefully you saw all the responses out there from these two folks. There are technical folks out here, but there were a couple that we were not able to answer, so I thought I would ask them right now. So one of the questions that came in that we didn't get a chance to answer was, can the optimizer use real component values? That's a great question.
Yes, they can. I probably should have covered that in the demonstration. So what can happen after you run the optimizer and you get those ideal component values that was a resistor of like 733.5 ohms, you can then switch it over and we have a discrete engine in the optimizer that can tell it to take the ideal value and then find the closest real discrete component value that you have available in your library to use as the final result. So it'll converge to unrealistic, very precision values, and then the next step would be to run the discrete engine to get your off-the-shelf discrete values.
Oh, great. Another question that came in was, can I use the mixed signal ability to simulate a PSpice circuit with real hardware?
Yes, you can. There's actually a video on our PSpice.com website that shows a couple of users with a Arduino processor board with some temperature and light sensors, and then PSpice is connected to the software running on that Arduino processor, connected up to a circuit in PSpice, so you can modify the feedback loop for that Arduino circuit running live. We also have other automotive customers that are using PSpice in that same sense to take an existing sensor in the vehicle, and then they want to redesign the processor and other sensors connected up to it for the whole system.
All right. This came from a customer who's using one of our competitor tools, LTSpice. And he asked, LTSpice allows me to add parasitics on passive like inductors and capacitors on the instance. I'm forced, so basically he's asking is, how do I actually do that with PSpice?
Oh, yes, we can do that as well. A lot of our users requested us to do that, so we listened to them. And in those modeling apps I was talking about earlier, we have modeling apps for resistors and capacitors and inductors, and some of the parameters in those modeling apps are the parasitics that you just mentioned. So all you need to do is just enter the parasitic values in, and then those will be built into the model and placed on the schematic.
Great. All right, I think one more, we'll go two more actually I can go through is, one is that I need to simulate noisy source in a time domain analysis. How do I do that?
Another thing we did with the modeling app, in those sources that I've added, one of the parameters for specific sources is noise that you can inject into the source. And then we also have a standalone noise generator that you can add alongside of your source to inject noise into your circuit.
So we have one more minute, so I'll ask one other question, and that is, I'm interested in finding timing violation of a digital portion of my circuit. Do I need to use another tool for timing budget, or can I do that with PSpice?
You can do it with PSpice. PSpice, the digital functionality in PSpice is actually quite powerful, and now that we've opened it up to all these other types of models like SystemC models, we're now going to start to leverage and refocus on some of these digital measurements. So for that sort of typing analysis, you can actually put into the tool, the model, the minimum max delays that you typically find in the data sheet, and then you can run a digital worst case simulation, and it'll produce, and it'll just, as an output of that, will produce the worst case timing value.
Thanks. So there's a couple of other questions, but what we'll do is we'll try to answer them on PSpice.com. So what we would like to, again, recommend you guys going to the PSpice.com, register yourself in there. You don't need any registration, but if you want to use the user forum, we would recommend that you register it. That's where you can chat with other users, designers, share data, and things like that. So we would encourage you to do that. And we'll also post this recording. I know a question came up is, will the recording will be available? We'll post the recording on PSpice.com, so you can also access the recording over there if you would like to share it with other colleagues. That being said, we'd like to thank you for your time and listening to this presentation. And if you have any follow-up questions, again, feel free to post them on pspice.com, and we'll be more than happy to answer them. So John, Alok, Gil, and everybody else, thanks for taking the time in this presentation and presenting this content. Really appreciate your time, as well as all the customers who joined this webinar. So thank you, and we will end this webinar.